Hello, welcome to the presentation of BWS, Best Window Selection based on sample scores for data pruning across broad ranges. We are Hoyoung Choi, Noyoung Ki, and Hyewon Jung, researching at Samsung Research Team and KAIST. This is overview of my presentation. At first, we analyzed two previous main approaches of subset selection. Then, we point out empirical and theoretical limitation of previous methods that shows each method only performs well at specific subset ratio. To resolve this limitation, we figure out that for a given subset ratio, there exists a desired level of difficulty for the subset. Next, we propose a novel algorithm BWS, which finds an outperforming subset in computationally efficient manner and achieves superior performance. First, we are going to introduce what is subset selection. Subset selection aims to find an informative subset S. The motivation is from large-scale dataset. Large-scale dataset enables huge development of machine learning, but it also involves some high computational cost and significant memory requirement. The goal is to approximate the performance of the entire dataset T. For example, a method named by forgetting score prunes 50% of Cyparten dataset without loss of performance. There are two main approaches for subset selection, score-based method and optimization-based method. The first main approach is score-based selection. This methodology assigns a difficulty score to each data and select high-scoring data. In other words, this method tries to select hard, atypical, and difficult data. The intuition is that easy data is redundant and possibly not important. But hard data located near the decision boundary might be beneficial. Here are two popular methods of score-based selection. Forgetting score is defined as the number of times during the training that the decision of the model is correct. Decision of the sample switches from correct one to an incorrect one. Here, ht-1x is output of the model at t-1's epoch, and htx is the output of the model at t's epoch. An EL2N score is defined as L2 distance between fx and y, where fx is the output of the model and y is label of the data. Second main approach of subset selection is optimization-based selection. This approach solves an optimization problem to find the core set, to find a subset that imitates characteristic of the entire dataset T, such as gradient and loss curvature. For example, ADA-core, adaptive second-order core set, finds a subset that imitates full gradient precondition with the Hessian matrix H. Another example, LCMAT, loss coverage matching, finds a subset S that imitates each gradient of the full dataset and eigenvalue of the Hessian matrix, which represent the curvature of the loss landscape. To help your understanding, we provide some real examples. Here are samples selected by forgetting score, representing the difficulty score-based selection, and LCMAT, which represent the optimization-based selection. The first row is car class and second row is dog class. As we can observe, samples selected by forgetting show some atypical features such as rotation and domain shift. Otherwise, samples selected by LCMAT shows representative features such as some clear characteristic of the class. We can figure out that two methodologies target different types of data. Next, we provide some empirical limitation of previous works. We benchmark three methods: random selection, forgetting score, and LCMAT. For each subset ratio from 1% to 90%, we select samples by each method and train a model with the selected subset. Then we check the test accuracy of the model. For example, this 66 indicates the test accuracy of a model which is trained by 30% random subset. As a result, forgetting, which represents the score-based selection, performs well at high subset ratio. And LCMAT, which represents the optimization-based selection, performs well at low subset ratio. However, we can observe that the most effective strategy varies depending on the subset ratio, and there is no single method that consistently outperforms across the entire range of subset ratio, from LCMAT to random and forgetting. So there is no single method that prevails the entire regime of subset ratio. We also provide a theoretical analysis that shows similar change of trends for the optimal selection. The problem setting is as follows. We assume that N data is sampled from normalized multi-normal distribution, and the label of the data is determined by sign of the first element. In other words, the true decision boundary is equal, the first element of X is 0. So X1 equals 0 is the true decision boundary. And we define difficulty score of data as 1 over absolute value of X1. So the data located closer to the decision boundary has higher score. We will select a subset S based on this score and train a linear regression model WS by solving this optimization problem. Then we evaluate the quality of S by observing first element of WS. This is because WS1 dominates the angle between WS and the decision boundary. As a result, if M, the size of subset, is smaller than square root D over LND, where D is the dimension of data distribution, WS1 is expressed as sum of absolute xi1. So data with big xi1, in other words, the easy data, results in better generalization. Otherwise, if M is bigger than D square LND, WS1 is expressed as sum of xi1 over sum of square of xi1. And this term has bigger value when xi1 has small value. In short, at sample deficient condition, the easiest data is the most beneficial, and at sample sufficient condition, the hardest data is the most beneficial. So data located far from the decision boundary, which is easy data, is beneficial at sample deficient condition, and hard data, which locates closer to decision boundary, is beneficial at sample sufficient condition. To summarize, in empirical setting, the outperforming methodology varies by the subset ratio. And also in theoretical analysis, selection strategy for optimal selection also varies by the subset ratio. Thus, our goal is to design a universal selection method, which prevails the entire range of subset ratio. In this section, we will talk about window selection or window subset, the flexible subset selection. We have a question about the intuition of previous method. Does training with hard or easy data enable the model to learn easier or harder data? To check this, we conduct training set split experiment. First, we sort the training data by difficulty score from easy one to hard one and generate 5 window subsets from the hardest 20% to the easiest 20%. Here, the window subset is defined as a subset consisting of samples with a contiguous ranking of difficulty. For example, the samples from this ranking to this ranking. Then we train a model with a single window subset and evaluate the classification accuracy for the other window subset. This figure shows the result. Each color represents the model, and y-axis is test accuracy of each window subset. For example, the orange lines represent models trained on 20% to 40% window. And these 5 points indicate test accuracy for the window subset the 5-window subset from hardest 20% to the easiest 20%. As a result, models trained on harder subset generally perform better across all subsets, with the only exception of the model trained on the hardest 20%. Right figure shows feature space of model trained on window. We can observe that the model trained on the hardest 20% does not generate the feature space well, while the model trained on 20% to 40% window generate the feature space well. This result implies that there exists an optimal difficulty level of the subset. Therefore, we expect that a subset composed of samples of preferred difficulty level will perform well. So we conduct sliding window experiment for CyParden dataset, and this is the result. X-axis is starting point of the window, and Y-axis is test accuracy of the model trained on the window subset. For example, this point indicates model trained on window subset 40% to 50%, and the accuracy is almost 82%. The result shows that for each subset ratio, there exists an outperforming window. This horizontal line is test accuracy for the random subset. And the optimal starting point of the window subset varies based on the subset size. As the subset size becomes larger, the window subset consisting of harder samples achieve higher performance. So from now on, we will call this window subset with optimal starting point as oracle window. For the ablation experiment, we also explore different types of subset. First, we search over all combination of two half-wide windows, denoted by this. Here is the result. Each axis indicates S1 and S2, the starting point of each window, and brighter color indicates higher accuracy. The best result occur when the two windows are close to each other. And second, we also search over random selection in wider window, which is defined as W% sample data from twice wider window. Also, horizontal lines are the result of the oracle window as we defined at previous slide. At higher subset ratio, the oracle window achieves better performance than the wider window. We can observe that there is small gap between oracle window and wider window. To summarize, we figure out that a single contiguous window subset achieves superior performance, and the ablation experiment also support the idea. Then there's remained question: how can we find the desired window subset or the window subset with optimal starting point in computationally efficient manner? To resolve the remaining problem, we propose best window selection, BWS. BWS find the near optimal window subset by solving KRR as the proxy task instead of training each window subset. Here, KRR is corner-ridge regression, which solves linear regression problem with feature extractor. Let's take a look at BWS step by step. At first, we sort data by difficulty score and create window subsets by sliding the starting point S. Then we obtain feature of the subset S with the feature extractor F. We denote the feature matrix as XS and the label vector as YS. So we sort data by difficulty score and create some window subset by sliding the starting point S and obtain the feature of the data with the feature extractor. Next, we calculate the WS by solving corner-ridge regression with S. In detail, we solve linear regression problem with obtained feature matrix and label vector. We obtain WS that minimize L2 distance between label vector and feature matrix time Y. And this is the regularization term. This regression problem has two closed form solutions expressed by this. Then we calculate classification of each WS for full training set and select S with the highest accuracy. In short, instead of training each window subset and checking the test accuracy, BWS solve kernel-rich regression with each window subset and check the classification accuracy for the train set. We sort data by the score, generate window subset by sliding point, and obtain feature metrics and label vector, solve linear regression problem with each window subset, and find the best performing window subset. Computational cost of BWS is directly related with cost for solving KRR from the step 3. And this cost is big O minimum D, n to power of 3, since the cost of the inversion of D by D matrix requires D to power 3. The cost is significantly low. For example, BWS only takes 10 seconds for Cyparten dataset. For the feature extractor, we train a model for few epochs on M randomly chosen samples. The reason that we conduct kernel-rich regression as the proxy task is that kernel-rich regression with the model-related kernels can provide a good approximation to the original model. So here is the experiment section. We conduct data pruning experiment for Cyparten, 100, and ImageNet dataset. We select data subset based on each method, train a model on the subset, and check the test accuracy. For Cyparten, we utilize ResNet 18, and for Cyper100 and ImageNet dataset, we utilize ResNet 50. The two blue lines, indicate Oracle window subset and the subset obtained by BWS. The other method prevail on specific region. For example, yield to score and forgetting, which represent scoring method, performs well at the high subset ratio. However, BWS outperforms the baselines across the broad ranges of subset ratio. In addition, BWS is also robust to label noise. We conduct data pruning experiment for noisy Cyparten dataset, which include 20% of random label noise. While score-based selection tends to include noisy data, BWS is robust to label noise due to its flexible selection. This is because noise data tends to have a high score since it is difficult to be learned for the model. At last, we provide cross-architecture experiment. Here is data pruning experiment for Cyparten dataset while using different architectures, convolutional neural network, and pre-trained VIT. As a result, BWS is also robust to changes in neural network architecture. BWS outperforms the baselines across the broad ranges of the subset ratio. As a conclusion, we figure out that for a given subset ratio, the desired difficulty level varies, and the window subset achieves superior performance because it is composed of the data with desired difficulty level. And BWS finds the optimal subset in computationally efficient manner by solving kernel-rich regression as a proxy task, and it achieves superior performance across broad range of subset ratio. As a future work, extension of subset selection to the complex dataset, such as very large dataset and unlabeled dataset, can be a promising problem. Thank you for listening my presentation. Thank you.